Hello. Yeah. Hello, everyone. Good afternoon. Those who are arriving from lunch, don't worry, you're just in time. Today, I'll be talking about building your own just-in-time compiler, or JIT for short. So, yeah. So, what is a compiler, right? There are basically two types of compilers. So, one is your ahead-of-time compiler, which is used by languages like C, C++, Rust, and stuff like that. So what it does is first compiles your code into machine code, and then you can run it how you want. Whereas a just-in-time compiler, it will execute while your code is running. So it will see how often you are calling some certain method, and then it will see if it's a hotspot, and based on certain number of times that you have called it, it will start compiling into machine code. And this is used by languages like Ruby, Python, Java, and yeah. So Ruby has had an interesting journey with compilers, just-in-time compilers. The first one that they had was MJIT, which, as Matt's mentioned today, was a good first start, but it did not compile Rails code into machine code, so we didn't really get a performance improvement where we want in our Ruby apps. And so that led to a new approach, uh, that led to the creation of a new technique for JIT compilation, which is called lazy basic block versioning. And this is the technique that is used by YJIT, and it's it's made JIT it's made JIT Ruby JIT a lot faster. And this was released in Ruby 3.0 and made on by default in Ruby 3.2. So with this method that they use, it is a lot faster, and they keep getting faster with each release. And so that's amazing. But there's another one which is called RJIT. So the interesting thing about this is that it's built in Ruby itself, unlike the other JIT compilers. So what it means is you can use this as just another class or gem and make this your own, and use this to make your own JIT compiler. So we'll take a look at that. Right. So when we say compile down to machine code, what is the machine? Which machine are we compiling to? Which machine are we compiling from? Right. So what is the machine? So there's basically two kinds of machines. One is your physical machine, which is your CPU. That could be your Intel Core i9, your Apple M2s, and the other one is a virtual machine that actually executes your code. So in the context of Ruby, that could be your Ruby VM, also called YARV for yet another Ruby VM. Yeah, so let's take a look at how these machines work under the hood. So first off, we have YARV. So let's say you have a simple program that does 1 plus 2. First, it will get translated into a certain instructions that the Ruby VM understands. So since YARV is a stack-based machine, what it means is that when you want to access certain values, you need to put those values onto a stack first, because that's how these stack-based machines work. So let's take a look at how it works. So PC is our program counter. It keeps track of where in the program we are right now. So right now we are at push 1. So we'll push 1 onto the stack. We'll increment the stack pointer, which keeps track of the top of the stack. So now we have push 2. And so once we have push 2, we go to add. And what happens is, uh, okay, right. So we push 2 onto the stack, and then we reach add. So when we reach add, we pop those two values from the stack, we take their sum, and then we push it back onto the stack. So this is how a simple addition works for the YARV machine. Now let's take a look at a physical machine. So a physical machine could be something that is register based. So a register is a simple unit of storage inside your CPU. So it's like the fastest way to access memory in a computer. So in a register based machine, there would be different kinds of instructions, and we have different kinds of registers. So over here we are moving one onto our R1 register, and when we go to the next instruction, we put R2, we move 2 onto R2, and when we call add R1 R2, the addition happens, but then the value gets stored in R1. So this is how it differs from your stack based machines. And this is basically how these two work with values. These two kind of machines, they work with values. Now let's take a look at, let's try and JIT compile a simple method that returns nil, right? Let's say we have a method foo that returns nil. So by the definition of our stack machine, we will first put nil onto the stack, and then we will return nil. But where does the nil go? Who are we returning nil to, right? Where are we returning nil from? So to look at this situation, we need to go deeper into the Ruby VM. So there are these instructions that the Ruby VM understands. They are called instruction sequences. So you can get these when you pass a parameter called dump equal to insns to any Ruby program, and it will give you a certain set of instructions that your Ruby code gets compiled into. Now, it will give you a certain number of blocks based on the number of methods you have and other things. I want you to focus on the block at the bottom where it says put nil and leave. So if you take a look here, the first put nil puts nil onto our stack, and then we leave from the method. But this is the same problem that we had before, where we don't know where we are leaving from, right? We don't know where we are leaving to. So for that, we need to take a look deeper into, we need to go even deeper at something that's called stack traces. So I'm sure most of you have seen report, an error report that's printed out when you don't handle an exception in Ruby. So it will give you certain things like the error value, the context from which you have rolled out from. So it will keep track of the path that your program has taken, and it will trace it all the way back to your top level. So we can use this to build something that we can use this to have context of our application. So how does this know that we are in a certain context in our program? So there's a data structure it uses that can keep track of everything. So one of the things that happens here is it keeps track of is which method you are in right now. It also keeps track of where in the program you are in right now. So you can see frames.rb and line number 2. And it also keeps track of what value you need to return. And all all this is contained within a certain struct for a certain level, and each level has its own context. So you can see for each level in our program we have these certain structures, and they need to be stacked, because if you are, let's say, uh, not handling an error from the top from the foo method, and you want to go all the way back to your top level, you can just keep popping your structure from a certain stack. So that way you go all the way to the top, and this is what's called a control frame. A control frame is just what I defined right now, and it has certain number of values within it. It will have the program counter that you can use to keep track of where in the program you are in right now. You can keep track of the stack pointer, so you can access the values from your stack. And it also contains the value of self. So if you do self dot something, it knows what the self means. And if you see the diagram on the right, the CFP just keeps track of which control frame you are in right now. So control frame pointer, that is CFP, and currently it's on foo. And when you go all the way to the top, you need to increment CFP essentially. So that way you can keep popping your CFPs, you can keep popping your control frames from your stack. All right, yeah, so like I said, if you want to leave from a context, from a method, you just pop its control frame, and yeah, that's how you return to something, right? Now let's take a look at how we can actually use these methods to build our JIT compiler. So I mentioned RJIT. So since RJIT is built in Ruby, we can use that to build our own JIT. Now let's actually do that. So RJIT provides a couple of things here. Uh, what's happening here is that we are replacing RJIT's compiler with our own compiler class. So we just need to write this class called JIT compiler, and we can provide this compile function in that class. So that way, RJIT makes it easy for us to write a JIT, and we don't need to uh, take care of all the boilerplate that's associated with writing a JIT. All right, so there's a lot going on here. I need you to focus on two things here. First off, are these constants. One is C, which provides you utilities to convert your values into something that the machine code understands. And the other one is INSNS, which is simply just a utility for fetching your YARV instructions and then using them as a simple object. And the other one is the compile function that I mentioned. You just need to write your compile function, and you handle the certain different instructions, and you can just compile them to assembly code here. We are using this assembler class for compiling them, but you can use any other gem like fiddle, which you can use to write machine code from your Ruby code. So yeah, so we are back at our method that returns nil, and it has two instructions, put nil and leave. So if we handle put nil here, first of all, we can see that we are fetching our instruction and making it an object that we can use. And then we are going over each instruction and seeing which kind of instruction it is. And based on that, we will write our assembly. So in the case of put nil, we want to put nil onto the stack. But since a physical machine is not stack based, it's rather register based. So we are mapping our registers to the values in the stack. So let's say you have two registers called R8 and R9. So, and we are putting them onto the stack, and our stack pointer is at the bottom. But when we do put nil, we put nil onto the value that's represented by the value at the stack. So let's say R8 is at the bottom of the stack right now, and stack pointer points to that. If you do assembly.move R8 and this value that is transferred into something that the assembly understands, then your nil will get stored into your R8 register, and then you increment your stack pointer. So this way, you are emulating a stack-based machine and using that to put values in your register-based machine. Right. Now, I talked about the leave instruction where we increment our control frame pointer. So to do that, there's two things that we need to do. We increment our CFP. We just add the size of a CFP to it. So we go to the next CFP. And we have this thing called execution context, which stores the current control frame that we are in right now. And it's the value of execution context. It's calculated as an offset from the value of CFP. It's just how the assembly works. So we need to follow that pattern here. Right, like I mentioned, CFP, let's say our CFP is at positions address 0. If we increment that, then we go to the next CFP. So essentially, we are popping a control frame from the top. Similarly, if we want to set the execution context, since we have incremented our CFP, we also need to set the execution context to the current CFP. So if we do this, we set the EC value to CFP, we now get the right, we now point to the right control frame. And finally, we get the topmost value from the stack and we push it onto the RAX register. What this means is that if you remember, Ruby has implicit returns. So if I just write nil and don't do return nil, it will still return that. So RAX is something that is used to return values, the RAX register. And so we just get the topmost value from the stack and we put it onto RAX. And then we finally return from our assembly using this asm.ret. Right, so like I mentioned, all the return values go to RAX, and that's how we return our values. So that's how we JIT compile our method that returns nil. Now let's take a look at something more complex than just returning nil. Let's say we have a method that returns a sum of 2 and 3. So if we get the instruction sequence for it, it would be put object 2, put object 3, and then it will add them. So in our stack-based machine, it gets 2, it puts it onto the stack, it puts 3 onto the stack. When it gets to plus, it pops them both. Here you can see it pops them both, adds them, and then puts it back onto the stack. And finally, we leave. So for put object, we get our values from the instruction, which is the first line here, where we're getting the operand, and we push it onto our register. We push this value onto our register, and then we just increment our stack pointer. For opt plus, I said that we need to pop these values. So what happens here is that since we have a register-based machine, we don't pop them, but we get those values from the registers, and we add them basically. And then we decrement the stack pointer because we can simply just rewrite our R9 register. And if you remember, I mentioned add R1 and R2, then the sum of them goes to R1, and so that's how we are emulating that that functionality. And that's basically it. That's how you JIT compile a simple addition method. But how fast is it? I mentioned JITs are faster than simply running your code. Here if we see the benchmarks, they are from Ruby Bench, which compares your performance from YJIT, from RJIT, and it compares them to a baseline of where you don't have your JIT enabled. So you can see YJIT can go more than up to 2 times as faster than without a JIT. And yeah, YJIT keeps improving in speed thanks to a lot of good work being done at Shopify. So thank you. And yeah, so let's have some fun with RJIT. I mentioned you can make this JIT your own. So let's see an example. Let's say I have a method called 2 plus 3, and if I run this, somehow I seem to be getting a 420, right? This doesn't make sense. I am not even monkey patching my integer class where I can change the functionality of that. So what's happening here, right? Well, I may have done something at the JIT level. So if you remember the opt plus instruction, where we were putting the sum onto our registers, instead of doing that, I just move 420 onto our registers, and so every time you add some value, all you get is 420. So this way you can monkey patch at the machine level. So it's blazingly fast monkey patching. And yeah, that's pretty much it. And last but not least, I want to thank Takashi Kokubun. This talk would not have been possible without his contributions, his help, and I highly suggest you take a look at this repository called Ruby JIT Challenge, and this is basically where I learned how to do this. And yeah, thank you.